Cool. Cool. Okay, guys. Thank you for attending today. My name is Rob, and I work for ECS Digital. ECS Digital is a DevOps consultancy. Sorry, I'm having some technical issues. Okay, let me start again. So, hi everyone, thank you for attending today. My name is Rob, and I work for ECS Digital. ECS Digital is a DevOps consultancy, and the aim of these playgrounds is to share knowledge about new technologies in the DevOps space. So before I dive right in, I would like to briefly talk about how this playground came to be. So personally, I must admit, for the longest time, I never really understood how HTTPS worked. I knew that the green lock in the corner of the browser was a good thing, but that was about it. Over many years as working as a consultant for ECS, I've noticed that HTTPS and certificates seem to be a recurring request for many clients. The majority of clients do not fully understand HTTPS, like I didn't, or just decide to treat them as a black box that they don't even want to understand. For example, they just think it's someone else's job. However, no one really wants to own up to their ignorance on the topic, because they are supposed to know it. It's a relatively fundamental thing, right? Personally, I did not study computer science at university, so I may have missed a few fundamental things, and I know I'm not alone in that respect within the industry. And for those that did study computer science, well, that could have been many years ago, and I know as well as anyone that people forget. So for these reasons, I thought it would be best to educate myself on the topic. And so the idea for this playground was born. So in this playground, we will start with a brief presentation that covers how HTTPS and certificates work, hopefully in simple terms. We will then proceed to a hands-on demo showing how we can deploy both internal and also production-ready HTTPS applications on the modern platform of choice, Kubernetes. Also a quick note, we will be using Kubernetes as the platform to deploy HTTPS applications. We will not be discussing how to secure communications within Kubernetes using TLS certificates. So that's just a small note there. Cool. So let's get straight into this presentation. So, HTTPS and certificates. So, the agenda for this presentation will be covering HTTPS, TLS, and certificates. We'll be talking about what each of these things are in detail. We'll be talking about public key cryptography, specifically public key encryption and digital signature. These are the underlying concepts that form the basis of HTTPS communication. We'll be talking about how certificates are issued, what are certificate authorities and certificate signing requests. We'll also go through diagrammatically the HTTPS workflow from a client's perspective. Also, what are self-signed certificates? You may have come across them before. What are they useful for? And also, what are their limitations? So what is HTTPS? Well, most people might be aware of what HTTP is. HTTP is the foundation of the World Wide Web. Communication between client computers and web servers is done by sending HTTP requests and then receiving HTTP responses. HTTPS is just the secure version of HTTP. So it stands for Hypertext Transfer Protocol Secure. In HTTPS, the security layer is added through something called TLS, or Transport Layer Security. Some of you might be more familiar with what is displayed in the top right there. Its predecessor, SSL, Secure Sockets Layer. Transport Layer Security is a protocol to encrypt communication between client and server. Your web browser, for example, and the server hosting the website you are looking to interact with. It ensures data transferred is private and secure, so any information sent from you to said website would be safe from prying eyes. It also acts to validate the authenticity of the destination web server using something called digital certificates. And TLS certificates are what give us the certainty that the website we are looking at is coming from a legitimate source. So what are certificates? A certificate is a digital document that acts as proof of identity on the web. It is how we prove that the party we are talking to, a website for example, is who they claim to be. So in other words, it allows us to be sure a website is being served from the true source, not someone impersonating that website. It contains information such as the domain name of the server we are trying to communicate with, and also importantly, the public key. So this is the public key of the server, and this is very important, as we'll see later on in this presentation and the hands-on demo. There's also other metadata associated with a certificate, including expiration time. Certificates don't last forever, and it's important that they are renewed regularly to keep things as secure as possible. The final note here is that certificates are signed by a certificate authority, and we'll touch more on certificate authorities in later slides. So some prior knowledge before we dive into certificates. We need to talk briefly about public key cryptography. So you need to trust that public key encryption and digital signature work. So these are actually the two principles that facilitate HTTPS communication. So the first principle is that any message encrypted with Alice's public key can only be decrypted with Alice's private key. So you might have seen a diagram similar to this previously. And then the second principle is that anyone with Alice's public key can verify a message was signed by Alice's private key. Okay, so I'm not going to go too in depth on this, but we just need to understand and trust that these two fundamental principles work. So how are certificates issued? So before we go into how certificates work from a client's perspective, it is useful to understand the steps that have been taken by the maintainer of the server that hosts the website you are looking to communicate with. How do they generate certificates to prove they are who they say they are? So in order to verify a website is legitimate, there needs to be some kind of entity or authority rather that everyone can trust that determines this legitimacy. And this is where certificate authorities come in. A certificate authority, or a CA for short, is a trusted entity that acts to verify identity on the internet. And this is verify, not proof. Certificates act as proof. They are a trusted third party, trusted by both the owner of the certificate and by the party relying on the certificate, the client basically. Certificate authorities issue certificates after verifying identity. So the CA is sometimes referred to as the issuer of the certificate. And this is important, as we'll see in the next slide. CAs are essentially, when you strip them back, just key pairs, or more specifically, a certificate and a private key. The certificate being just a wrapper around the public key. And then the final note here is that your browser automatically trusts a list of predefined CAs. So when navigating to a website, your browser tries to verify the certificate of the website against a predefined list of certificate authorities built into the browser. So these are stored in your browser, and on your behalf, your browser will trust these. So you don't even know this is happening. This is often referred to as your browser's trust store. Some common root authorities are DigiSign, VeriSign, IdenTrust, but most big organizations will have their own certificate authority. Certificate signing requests. So a certificate signing request, or a CSR for short, is how we go about requesting certificates from a server perspective. So this is a message sent from a subject. You can think of the subject as being the web server hosting the website, to an issuer, the issuer being the certificate authority, in order to apply for a certificate. The CSR, or the certificate signing request, contains information such as the common name, or the domain name in most cases, and the public key of the applicant, or the subject. If the CA is happy with the information provided, the CSR is signed by the private key of the CA to issue a certificate. So the CA determines if it is happy through challenges, but not to worry too much about that. That's a little bit out of scope of this presentation. A certificate is then sent back to the subject. The subject can now use this as proof of identity on the internet. So here's a diagram to sort of illustrate the point. So here we have the web server, or the server hosting youtube.com. And on the right hand side, we have a certificate authority. The certificate authority here we've called Google CA. I've just done that for ease of understanding. It's not necessarily called Google CA, but you can think Google does have CAs. Let's just call it Google CA here for ease of understanding. So when the communication begins, YouTube will say to the Google CA, I want to use HTTPS from now on when I'm delivering content to my clients. I have created a CSR with my public key. Can you please sign it? The Google CA will respond, sure, I have signed your request with my private key, thus generating a certificate. Anyone who has access to my public key can verify it was me who signed the certificate. So we saw in the previous slide that the browser has a list of trusted trusted CAs that it trusts on your behalf. When the browser is accessing youtube.com, youtube.com will provide the browser with its certificate, which was signed by the Google CA. So therefore we have the public the public key of youtube.com. We also have the public key of Google CA stored in our browser by default, and therefore we can prove identity on the web. So as this diagram visualizes, all a certificate authority is a key pair owned by someone else. So in this case, this is Google CA's key pair. All browsers come with a list of certificates, or more specifically, public keys that are trusted by default. One of them being the Google certificate authority, or what it is actually named. Because the browser has the public key of the Google certificate authority and trusts this key, it will use the public key to verify the certificate for youtube.com was signed by Google CA. And if it's signed by Google CA, the browser knows we can trust the certificate. And therefore we can prove that youtube.com is being delivered from a legitimate source. I also want to briefly talk about certificate chains. I don't want to spend too long on this, but the last slide gave us a diagrammatic example of how things might work, but it was a very simplistic view of how things work. In reality, there's usually more levels than just one CA and one certificate. So there's usually this concept of intermediate certificate authorities. So I found this diagram online, and I thought I would sort of annotate it a little bit so it's easier to understand. So here we can see that I've circled in blue. We have a root certificate authority and an intermediate certificate authority, and then finally we have the identity certificate. So this is the certificate that is provided by youtube.com to the clients to prove that youtube.com is youtube.com. That's the identity certificate. But usually there'll be one or more intermediary CAs that are between that certificate and the root CA. So the way we need to understand it is that the root CA is actually a self-signed certificate. So the certificate for the root CA is a self-signed certificate. So we have a public key and a private key. The private key signs the public key. So it's the same private key for the root CA, signs the public key to create a root certificate. But then for every intermediate certificate, the certificate is signed by the private key one level up or down, depending on how you want to think of it. So you see here, the intermediate certificate is signed by the root private key. And then the identity certificate is signed by the intermediary private key, denoted by the issuer private key here. So, how does HTTPS actually work? We've seen how certificates are issued, but how do they work from a client's perspective, and how do they fit into the HTTPS workflow? So again, let's have another diagram to try and understand this. So in this case, on the left-hand side, we've got your browser. On the right-hand side, we have youtube.com. So we saw in the previous diagram that youtube.com requested a signed certificate from a certificate authority. They got that, and now they can deliver content securely to your browser. And this is the communication workflow. Your browser will say to youtube.com, please give me HTTPS youtube.com. So we want youtube.com, but we want to make sure that it's been delivered from a legitimate source, hence the HTTPS. Sure, here's my certificate containing my public key. It was signed by Google CA. Then your browser will say, I know and trust Google CA. I will verify this certificate with the Google CA public key, which should be built into your browser by default and trusted by your browser by default. Then, once it's been verified, your browser will say back, I have verified your identity with Google CA's public key. I can confirm you are who you say you are, and I've created a new symmetric key and encrypted it with your public key. So this symmetric key will be useful later on for encrypted all information to and from the browser and youtube.com. So youtube.com says, smart choice, only I have the private key to decrypt this. Because remember, we, or our browser, encrypted this symmetric key with the public key of youtube.com. And from the principles of public key encryption, only the private key can decrypt information encrypted with the public key. And therefore youtube.com now has the symmetric key. And now we are the only two machines on the entire internet who know this symmetric key. So from now on, let's encrypt all communication with this key. So we see here HTTPS has not only proved the identity of youtube.com to our browser, so we're sure it's coming from a legitimate source, but we're also then able to secure communication to and from your browser and the server with a symmetric key that no one else on the internet knows. So everything is encrypted, everything is secure. So we've now covered how certificates work in an ideal production workflow. However, there's quite a lot of complexity and setup required if we just want to develop or, let's say, test in internal environments. So this is where self-signed certificates are useful. So I'm sure many of you have come across self-signed certificates before, potentially in tutorials that gloss over the more productionized stuff. So A self-signed certificate is a certificate that is not signed by a publicly trusted certificate authority. Instead, they are signed by a key pair that you control. So what will actually happen is when you generate a set of self-signed certificates in the background, away from your eyes, away from human eyes, the steps below will be sort of done for us in the background. So you'll start with a private key and a public key. The private key signs the public key, and then we'll end up with a private key and a certificate. And obviously the certificate is just a wrapper around the public key. It's just a signed public key. So it's worth noting that self-signed certificates are good for internal environments. However, should not be used for public-facing applications. So it makes sense that external browsers will not trust these certificates, and therefore they cannot verify who signed these certificates. So it's not going to be trusted by external browsers. So one final example here, it's going to be very simple to the CA example diagram that we saw before. So here on the left-hand side, we have your application deployed to a staging environment or a development environment, let's say. And on the right-hand side, instead of the Google CA, we have our own CA, which is essentially just a key pair that you own. So the workflow is very similar. You request to have your CSR signed with the public key of the CA, and then the response is the certificate signed by the private key of the CA. So in this case, if you have a second internal application that wants to communicate with the primary application, initially it won't be able to do so, right? Not until we have provided it with the public key or the certificate of the CA that we've created, the self-signed certificates that we've created. Once we provide it with that information, then we can trust the communication, and we've established HTTPS in an internal environment. So, thank you for listening to the presentation. Now on to the hands-on demo. So, just waiting for a link to the playground. Just need someone to share with me the link to my credentials, because they weren't generated before this started. Just while that is happening, I'll briefly talk through what we will do in this hands-on section. So the hands-on part of this playground is a tutorial that will cover the steps required to deploy both an internal and production-ready HTTPS application on a pre-existing Kubernetes cluster. And this cluster was built on Azure Kubernetes Service, AKS. If you want the code to generate this cluster for yourself, you can actually take a closer look at some of these other directories here. So it has everything included, not only the hands-on tutorial, but also all the infrastructure used to create this playground. So just waiting for the credentials. Maybe this will work. Okay, cool. So cool. Okay, so let's make a start on this hands-on section. So the initial setup would be to either SSH into your workstation, but what we are going to do is actually just navigate to the link that was provided to you. Then we can enter the password. And then we should be logged into our workstation. So all of the work that we're going to be doing or the majority of the work that we're going to be doing for this hands-on section is going to be done in this workstation. Okay, so the first step that we need to take is we need to clone down this repository. So if you have access to this repository, please clone it down. Then the next step is we need to step into that repository. So we can do that using the cd command, change directory. And then we have all our resources available to us. Okay. So in order to deploy our HTTPS application, we will need to utilize the Ingress resource available by default in Kubernetes. So the Ingress resource exposes HTTP and HTTPS routes from outside the cluster to services within the cluster. So here's a neat little diagram sort of trying to talk you guys through how that works. But for the built-in Ingress resource to work, the cluster must have a Ingress controller running. But the Ingress controller is not installed by default on within Kubernetes. So when we create a cluster within Kubernetes, it's not installed by default. So the most popular controller is provided by Nginx, and we can add this to our cluster using Helm. It's also worth noting that the Ingress controller is what is used to fulfill the mapping of any Ingress routes that we define. So we may define our Ingress routes in Kubernetes manifests, for example. So I've said that we can add this to our cluster using Helm. For those of you who are not aware, Helm is the de facto package manager for Kubernetes. So it makes it much easier for us to deploy pre-packaged applications to Kubernetes. So the first step that we will take is we will add the Ingress Nginx repository to Helm on our workstation. So if you copy and paste the first command here, feel free to type it out if you wish, but it's probably easier to copy and paste. So once you run this command successfully, we'll see something like that, the response here, just telling us that this has been added to our list of repositories successfully. The next step is that we will use Helm to deploy the Nginx Ingress controller. So we can do that using this command. So I will run this command, and whilst I run it, I will explain. So this command has a few additional parameters that I've included. So the Kubernetes cluster that we are interacting with in this session. So each of you has your own workstation, but each of you will also have your own isolated namespace within Kubernetes. So you'll be interacting with one Kubernetes cluster. However, you will not be able to interfere with anyone else's cluster or anyone else's namespace, because you all have your own namespace. So you're all working in your own isolated environment. And because this is the case, some of these variables needed to be set to set the scope of the Ingress controller. So here, the first two parameters are to make sure that the scope of the Ingress controller is restricted to the namespace. So each of you are going to be generating your own Ingress controller. No one will share an Ingress controller. It will all be specific to your namespace. This final parameter here is an admission webhooks parameter. So this is actually installing stuff at the cluster level, and because we only want to install the Ingress controller at the namespace level, we want to set this to false. So if this command runs successfully, you will see something along the lines of this with an example ingress, showing that we can start including ingresses. So we can start creating manifests that include the ingress resource, which is good, and we will be doing that. So once this is deployed, we can view the created service and associated external IP. Note that this may take a few seconds to generate, but because I've been talking, it should be there. I'll make this a bit bigger. So we can see here that we have an external IP generated. So this external IP actually acts as the entry point for the outside world into our Kubernetes cluster. So this is very important. And because that is the case, we will set this as a variable for later use. So that's all that this command is doing here, is setting the external IP to be the external IP represented here, using an awk command to basically extract that. So if we were to echo external IP, it should just be that IP address. Okay. So first thing we want to do is we want to create an internal app, and we want to secure this app using self-signed certificates. So we can generate self-signed certificates using Openssl. So Openssl is a tool that is installed by default in most Linux distributions, including Ubuntu, which we are using. And we'll use the following command to generate some self-signed certificates. So it will be a private key and a certificate, which is, as we've said before, a wrapper around a public key. So if we copy this and paste it, and then explain the command. So as you can see here, we have two outputs. One output being the certificate, which we've stored in the temp directory. And similarly, we have the private key, tls.key. We also have the subject. So this is the domain that we are creating these self-signed certificates for. So here we've got dpgexample.com. So that's just an abbreviation for DevOps Playground example. There's a few flags at the top also of note. So X509 is basically the format of the certificate. Node, it says nodes, but it actually stands for no DES. So this basically means that the private key that we're outputting is not going to be encrypted. So no DES means do not encrypt the private key. Days, this is basically saying that our certificate is going to be valid for 365 days or 1 year. And then also at the end, we have the encryption type that we'll be using. So after generating those using Openssl, what we need to do is we need to create a corresponding Kubernetes secret. So if we copy the next command, what this next command will do is it will create a secret within Kubernetes, a TLS secret within Kubernetes, and this is a specific type of secret that we can specify the certificate and the key that we generated before using the Openssl command. I also want to mention as we go through this hands-on section of the course that I'm not going to be diving deep into how Kubernetes works. That there is a little bit of prior knowledge assumed, but anyone should be able to follow along with the commands, and I will try and explain them as best I can, even for people who are not necessarily as familiar with Kubernetes. So kubectl is actually the command line interface that allows us to interact with our Kubernetes cluster and create resources. So here we're creating a secret resource, and the TLS, secret TLS is a specific type of secret resource that deals with TLS certificates. So when that's successfully created, you will see an output similar to the following here. The next thing we will do is we will actually run the demo application. So we will create a demo application for us to navigate to and see if we have secured our application with HTTPS correctly at the end of it. So let me run this command and at the same time show you guys what's going on here. So this is actually applying a manifest. So you see here, kubectl apply is how we apply manifests which define multiple resources in most cases, and they're in the form of a file. So here it's a YAML file. It's always usually a YAML file for configuring Kubernetes, and it's within the self-signed directory within the repository. So if we look here, what this manifest describes is a basic deployment and a corresponding service. So don't worry too much about this. This is quite basic stuff. The main things of note here is that we're deploying a container image. This is a very basic container image. It's just a hello world image, and we can actually modify the text that will be displayed on this hello world application via an environment variable. And here the environment variable will display something like this: welcome to your internal app. It's been secured by self-signed certificates. Okay. So after running that command, we can see that we successfully created the deployment resource within Kubernetes, and we also successfully created the service resource within Kubernetes for our internal application. The next thing we need to do is we need to create the Ingress resource. This is going to allow people from the outside world access to our application within the Kubernetes cluster. So for this one, you can see here we're creating an Ingress resource. And a few important things to note here within the manifest is that we're defining the domain name that we wish to associate this Ingress with, and also the secret name that we created before. So remember, before we created a Kubernetes secret. This secret name includes the certificate and private key associated with the self-signed certificates we're looking to use to secure the communication to DPG example and make sure that HTTPS will be working for that domain. Yep. So let's apply that. And once you apply, you will see that your Ingress is being configured. Then finally, what we can do is we can test the Ingress configuration. So we can do that using this curl command. So this curl command, what it will do is it will actually hit dpgexample.com. And it will hit it over HTTPS. So the default port for HTTPS is 443. So the above curl command, we actually indicate that we trust the self-signed certificate as an internal CA. So here we are providing a CA cert flag, and this is actually just the certificate, because we're using self-signed certificates that we created before. So if we run this command, we should get a curl response, a text response of the web page that we've created. And as you can see here, we have the text that we saw within our Kubernetes manifest. Now, some of you may not be satisfied with this text response. You might want to actually see things in action in the browser. So alternatively, on your own machine, this is not your workstation, so not in your Wetty terminal, but on your own machine, you can modify the host file on your machine, your laptop, and view in the browser. But this will require sudo access. So if you're dialed into this playground via some kind of VPN, you may not be able to do this, or if you have restrictions on your work laptop, for example. So bear in mind, you guys don't have to do this, but as an example, I will show you how this can be done. So what I'm going to do is I'm going to modify the host file, which is located at etc hosts. And you can see here it requires sudo access. But you might be able to see I've done something similar to this before. So we can actually add the host of our Ingress controller and correspond that to the domain that we have defined in our Ingress resource within Kubernetes. So let us do that. So what I will need to do is I'll need to echo out the external IP. And this is the IP that we must associate with the domain. And then if we save the file, we should now be able to navigate to dpg example.com. But you will notice we have managed to navigate there, but it's given us a warning, right? So we're getting a warning from our browser saying basically we do not trust this website. We can't trust it because we don't trust the certificate was signed by a trusted certificate authority, because it was signed by a key that we created, not a key that's trusted by default by our browser. So some browsers will let you just press proceed anyway. If you're using Safari or Edge, it might allow you to do that. But sometimes on Chrome, you get something like this, and you don't get an easy way to proceed. But what you can do is just type into the browser. You won't actually see yourself typing, but you can type "this is unsafe," and then you can see here we've navigated to our HTTPS application. So welcome to your internal app. This has been secured with self-signed certificates. Cool. But as you can see, this is not secure. It's not trusted by our browser. So that's why we move on to the next section, which is a production application. So the first step here is we're going to have to log into Azure. So we can do that with this command. So don't worry too much about this. This is just how we log into Azure. Service principals are basically just accounts that I've created for you guys to interact with Azure. And then what we need to do is we need to configure a fully qualified domain name for the Ingress controller external IP. Okay, so what does that mean? Well, let's take a step back. Because our Kubernetes cluster is hosted on Azure AKS, during the installation of the Ingress controller, an Azure public IP address is actually created that corresponds to the service external IP. And we can associate this Azure public IP with a fully qualified domain name. So in Azure, so here, for example, this is, I don't know whose this is, but what this has done is it's been created when you create your Ingress controller within your Kubernetes cluster, and it has an IP address here. This will be corresponding to an external IP address of one of you guys. I could probably find mine if I wanted to, but that's beside the point. The important thing is that we can associate a DNS name here, and what we can do in Azure is if we have a DNS name, we can actually create a fully qualified domain name that is unique, that we can then set up HTTPS with. So how are we going to do that? So again, this is a duplicated step, but I wanted each section to be, you could work through them in isolation or as one thing together. So we'll set the external IP again, even though we have already done this. The next thing we need to do is associate the public IP address with a DNS name. So for the purpose of this playground, we will use the host name of our workstation as an example. So in my case, the host name is arriving walleye. You guys will have some comical name as well. The next thing that we do is we set another variable, and this variable is actually the resource ID of the public IP address within Azure. So we don't need to worry too much about this command. Just know that it's setting it to the resource ID within Azure. Okay. So if we were to echo this, it's going to be a long ID. And as you can see here, it's a fully qualified, if you will, ID. Next, we need to update the public IP address with the DNS name. So we can do that using the Azure CLI. So when we're using the AZ command, that's actually the Azure CLI we're using, which allows us to interact with the with Azure resources from the command line. So this might take a minute or two to work, but there it is. So what this will do is it will update your public IP with a DNS name. So remember I was saying before, if I update this, whoever this is, if they've done it correctly, you should see a DNS name, right? Cool. So everyone's following along, that's good news. Okay, and then what we want to do is display the fully qualified domain name. So we've generated a fully qualified domain name now, but what we want to do is we want to display this in the terminal. So we did actually just see it then in the Azure console, but let's also view it in the terminal. So this is going to be our unique fully qualified domain name that we're going to use for our HTTPS production application. So we will actually set this as a variable for later use as well. Okay. So we now have a unique fully qualified domain name we can use for our application. Good. So that prior stuff's out of the way. So now we need to deploy a demo application or the production application to the Kubernetes cluster. So we do this using Kubernetes manifests again. So let's take a look at our Kubernetes manifest. This time it's nested in the LetsEncrypt directory, and we'll talk a bit more about LetsEncrypt in a second. But let's first look at our production application YAML file, or our production application manifest. As you can see, it's very, very similar to our internal application. However, this time the environment variable has changed to welcome to your production app, certificates signed by LetsEncrypt. So that gives you a clue as to how we're going to generate our certificates. They're no longer self-signed. Also, it's worth noting within this manifest we have the corresponding service also. So let's run this. And if it is successful, you will see that your deployment and service have been created. The next thing we need to do is we need to issue certificates and configure the Ingress. So this is going to be slightly different to last time when we were doing things with self-signed certificates. So it's worth noting that prior to this interactive session, so prior to this playground, the Kubernetes cert manager controller has been pre-installed on the Kubernetes cluster. So this is something that I have done prior to this session to allow us to automate the generation of certificates. You can actually see within the AKS cluster directory for details on this. So if we take a quick look, I'll show you the steps taken to do this. So here is the Terraform code that used to create our AKS cluster, but then there's some additional steps here to deploy the cert manager, and I obviously used Helm to do this because it was the easiest way. So there's just some steps here if you wanted to replicate that. But it's important because Cert Manager, the Cert Manager add-on, is what allows us to automate the management and issuance of TLS certificates from external CAs. You can actually do it from various issuing sources, but it's important that we can do it from external CAs, right? So actually had a thing here. So supported issuer types for the Kubernetes Cert Manager. So you can actually automate self-signed certificates as well if you wanted to, but we did that manually just to sort of go through that. But you can also set up a CA of your choice. We can use Vault. If any of you are familiar with HashiCorp Vault as a CA, we can use that as a supported issuer within Cert Manager. But the one that we're going to be using is Acme. So we'll talk more about what Acme is in a second. So let's create our issuer, and whilst we do that, we will talk through the manifest. So again, we're in our LetsEncrypt directory. So a few key points of this manifest. So the issuer resource within Kubernetes is not available by default. This is only available to us because I have installed the Cert Manager add-on prior to this session. So an issuer is a custom resource made available through the Cert Manager controller. Issuers basically represent certificate authorities and allow us to automate the generation of certificates. So it allows us to automate that. And notice I've called this resource LetsEncrypt, and that's because we are actually using something called the Automatic Certificates Management Environment Protocol in order to generate certificates here. And ACME, the Automatic Certificate Management Environment Protocol, is the underlying protocol of the LetsEncrypt CA. What is LetsEncrypt, you might ask? It's actually a non-profit certificate authority providing TLS certificates to many websites across the web. And how does it work? Well, the objective of LetsEncrypt and the ACME protocol in general is to make it possible to set up a HTTPS server and have it automatically obtain a browser-trusted certificate without any human intervention. So this sounds great. This sounds like exactly what we would want in a Kubernetes-style world. So you can see here that there is an ACME field within the issuer that allows us to define the server that we're going to interact with. So this is the LetsEncrypt ACME server. It also requires a temporary email in order to do this. So this was just something I spun up quickly using temp mail. It's gibberish really, but it's a valid email, so we can use it. And then, yeah, I think that's all worth of note there. So let's make sure that we ran this command to create our issuer. Yes, so our issuer has been created. The next step is we need to update the Ingress manifest to use our fully qualified domain name. So the Ingress manifest is going to be actually quite similar to our self-signed Ingress manifest. However, there's a few changes. So in our self-signed internal application, the manifest for Ingress used the DPG example domain that we were using. All of us were using that domain, right? Because we were using self-signed certificates. Now we need it to be unique because this domain name is going to be corresponding with certificates that are trusted by the CA built into our browsers, right? So for a production application, we need a unique, fully qualified domain name that is corresponding with its own certificate, right? That you guys will be creating and automating using Kubernetes. So the hosts here will actually be the fully qualified domain name that we created beforehand. So that's why it has the replace me text here. The secret name, TLS secret, is actually something that's automatically generated for us when we're using the issuer resource. So because we have the issuer resource, whenever we create an ingress, it will automatically create this TLS secret for us. and this TLS secret will contain, as we manually did before, a certificate and a private key. So let's use this sed command here. So for those of you who are not so familiar with sed, it's just basically sort of like a find and replace tool. And what it will do is it will allow us to find and replace and update our manifest with the fully qualified domain name that we defined previously. So now you can see that the fully qualified domain name is here. And yours will be your fully qualified domain name. So that's good. And now, because we've updated that, we are in a position to apply that manifest. So let's run apply. So if successful, you will see this. The Ingress resource has been created, so this is all good. Finally, coming to the end now, we can verify the certificate was created successfully by checking the status of the certificate resource here. So this may take a second to come through, but because there's lots of stuff happening in the background, but mine's already come through. So some of you might be seeing false, but if you just give it a few seconds, it should eventually come back as true, provided you've worked through all the steps correctly, of course. So when this comes back as true, we're actually ready now to see application with HTTPS working within the browser. But before we do that, I think one other useful thing that I like to look at is I like to describe the certificate resource. So here, certificate resource is obviously another custom resource definition provided by the Cert Manager add-on. We can actually use kubectl to describe to get more information about that certificate. And I think it's a good thing to do because it illustrates the point, some of the points I made in the presentation. So these are the steps that were taken. So initially, the certificate is attempted to be issued. But what I think is quite interesting is that the certificate manager actually creates a resource called a certificate request. So this certificate request, as we've seen before, is similar to like a certificate signing request within the presentation. Finally, if we echo out our fully qualified domain name and copy this and paste it into our browser, voila, we have a HTTPS application fully secured with certificates, trusted by our browser by default. So we have a valid certificate here, really good, productionized application. Welcome to your production app, certificate signed by LetsEncrypt. Cool. So no longer self-signed. The certificate was automatically generated using the Cert Manager add-on within the Kubernetes cluster, but we created the resources that were required in order to generate the certificate. So those being the issuer resource, as we saw here. And what the issuer does is it watches for new ingresses being created. We also then went ahead and created an ingress which matched up with our fully qualified domain name. And then the rest is just managed by Kubernetes. It's actually so easy. All we needed was to spin up that issuer, and Kubernetes goes about creating your certificate, and in the background it creates a certificate signing request, a certificate request, sorry. It also creates some other resources, but it does it all in the background, so you're all sort of taken away from it, and it makes everything super easy. So hopefully you can agree that that was a relatively pain-free process and is not too difficult to replicate in the future. So to summarize, we've seen how we can deploy HTTPS applications on Kubernetes. We secured an internal application using our own self-signed certificates. And then for production, we automated the issuance of certificates signed by a trusted CA, in our case, LetsEncrypt, using this Kubernetes Cert Manager add-on. Cool. And that's pretty much it from me. Any questions? I do have a question slide somewhere. Any questions? Okay, so it doesn't seem like there's any questions. So I guess we'll wrap up there. Thank you for attending, guys. Really appreciate it. Hopefully you learned some good stuff there. And yeah, good luck HTTPSing in the future. Oh, sorry, I do have one question. What happens if certificate and keys are compromised? Right, so if a man in the middle gets access to your certificate or your public key, that's not too much of an issue. The real issue is if they gain access to the private key. The private key is what decrypts any information encrypted by the public key. So in theory, there should never be a case where the private key is communicated over, is in the communication between the client and the server. So it's very unlikely that that would happen. Is there a possibility of public keys being falsified? So not really. So basically the public key, there is only one public key with the associated private key, right? So from a CA's perspective, that public key is wrapped up in a certificate and stored in your browser by default. So that public key cannot be falsified because if it was a false public key, it wouldn't then go ahead and decrypt that certificate from the website hosting the application you're looking to interact with. Any more questions? Okay, that's all from me, guys. Like I said, hope you managed to learn something from this session, and good luck with HTTPS in the future. Sorry, we've got another question. So can I implement key or cert rotation? Yes, this is something that you can do, and it's something that you can automate within Kubernetes. although it is slightly at the scope of this presentation, but yes, it is something that you can do, and it's something that also that you should do. It's often best to keep the life cycle of certificates as short as possible. So rotating the certificate and keys is as often as possible is the correct thing to do, and this can be automated in Kubernetes, like I say. Okay, so I've been told that I can finally actually wrap up. So yeah, so hope you learned something from this session, guys, and good luck HTTPSing in the future. Thank you.